So the agenda, so I'm going to briefly talk about the reinforcement learning. So it's very quick overview, and then some of the examples of reinforcement learning applications. And then particularly, I like to highlight the human factors in the deployment of reinforcement learning systems. And then I will redirect attention to self-supervised learning, and then giving you an example of self-supervised learning application, and also try to establish some connections between self-supervised learning and reinforcement learning. So hope you find that interesting. Yeah, so as you know, the Amazon has been in deploying machine learning system in production for over 20 years now. So if you just look at the supply chain, which is probably the most famous part of the Amazon.com, if you look at the traditional supply chain, so what happens is it's more like reactive. So everything, so when the order comes in, the vendor starts to react to the orders, and then the shipments, the carrier start to react to the shipments request, and the fulfill center start to prepare the fulfillment. And then, so it's such a reactive system often cause delays and human handing over. And there's a lot of the excessive amount of resources and time has been spent on handling through manual operations. So at Amazon, actually over 99% of the inventory it's replenished through automation. It's not actually triggered by any ordering systems. Right, so that's quite fascinating to me. So essentially, what we are trying to do is we're considering the retail operations as a manufacturing. So we are trying to automate and then provide an end-to-end solution. So this starts from forecast. So forecast for both demand and supply, and then everything is actually calculated and predicted and planned in advance through automations. So this is including the procurement, the placement, and the fulfillment. So there's probably little room for human touches. And then the only places where human plays an important role is overwriting those decisions made by machines. So that way you can actually really cut the cost. So streamline your operations. So that's just a warm-up story on the importance of automation and decision making. So now let's look at the reinforcement learning. I assume that some of you may have seen such diagrams. So this is quite a popular diagram showing on the left is it's a very simple diagram showing the interactions between an agent and an environment. So the agent will observe some states from the environment, and then based on the observation, the agent will then decide to take some actions. The actions themselves will actually have an impact on the environment, which will then produce the next states. And so this cycle goes on like this. So this is an ideal situation where most of the current RL research has been focused on. But in reality, actually, the nature, the environment, this can be quite hard to model. And so the dynamics of your environment the system dynamics in your environment often has lots of noises, so disturbances, variabilities. So some say that you don't have predictability until you understand the variability of your system. And there's also a lot of constraints. and uncertainties. So all these has made the environment is hard to model and predict. And yet, from the control theory point of view, that's exactly where a good controller needs to achieve. A good controller needs to produce a set of controls to the dynamics, and given such disturbances and constraints, and then try to achieve a long-term cost reduction, but also make sure that the system is within the range, so it's controllable, it's stable. So I guess the reason I put both up here is because I think both of them are quite important, and then they are similar, and then the control diagram is somewhat resembles the reality, and whereas the RL, current agent environment interactions, it's where most of the research has been focused on. So it would be nice to combine the two. On the bottom left, you see some links. So the first one is in order to make sure that the environment has been really, reflecting and representing the true reality. So Amazon has recently open sourced a supply chain simulator. So essentially, you can simulate your supply chain. So rather complicated supply chain networks through this open source, and then you can train your agent to take various actions, such as keep the inventory levels and moving some items from warehouse to fulfillment center before the order comes in, things like that. So that's one of the very interesting open source you might want to have a look. The other one is that my team members and myself has been contributing a series of RL-based environment, and so one of them is the energy storage system. So this energy arbitrage system where you can sell the actual energy back to the grid, and based on the demand and supply, and also the fluctuations of the price on the market, and you can develop some agent to do that. So this open source gives you a simulator to simulate the system dynamics. So that's basically very high level overview of the reinforcement learning. The next one is one of the key concepts within machine learning. It's called Markov Decision Process. And then, so essentially it's a state transition diagram. So here we are trying to play the Pong game. The Pong game, perhaps many of us have played. So essentially you might make sure that the ball here, you can just always try to shield the ball so that it doesn't go through your end of the your end of here and here, and then but the ball will bounce on the two horizontal edges here. So the goal is to move up and down. So it's supposed to control the green one. So the only action that you can exert on this command is actually just move up or move down based on the situation. And then so what happens is that the MDP provides a abstraction of such decision making. So essentially what depicted here, the green circle is the states. So it's essentially it's a snapshot of the screen of the raw pixels. And then on the states, you can choose several actions. So in this case, there's a A0, A1. I guess in this example, maybe A0 meant going up, A1 means going down. So interestingly, when you take some actions, there is a stochasticity here. So when you take A0, there's a probability distribution where you might end up. So there's a 20% chance that you end up in a state S2, and then there's a 10% chance you going back to states 1, original states, and then 70% chance you go to states S0. And so these are completely stochastic. And then so another good example would be if you driving a boat or something in the water, in the ocean, and so when you turn left 45 degree, and then the wind might blow you another 20 degree, and those are some of the disturbances that you experience from the environment. And then most likely there's a maybe stationary or maybe non-stationary probability distribution where you will transition to different states based on actions. So so the idea is that you're taking a series of actions, and then towards the end of the game, you maximize your rewards. So in this case, if you end up in the state S0, then you'll get 5 points. But if you go into other states, you won't get any points. And then if you're in state S2 and you take action A1, and 30% chance you actually will lose 1 point. And then the idea of reinforcement learning is trying to figure out a policy where for each state, you know exactly where you should take actions such that the overall accumulated reward is maximized. So hopefully that gives you the basic idea about MDP and reinforcement learning. So something very interesting here is that maybe you can think this is very interesting. So I could just learn how experts have done. So that's the supervised learning. So whenever there's a state, there's an action taken by the expert. So in this case, if I record how Formula One drivers drive their trajectory, and then which show as a blue color, then I can just basically record a series of state state action pairs, and then learn the mapping between state actions. Well, excuse me. So the issue here is that there is a big difference between supervised learning and RL. Is that in reinforcement learning, the data is actually generated by your action. So essentially, if you have a little deviation from the experts, let's say here, normally this would be okay because in supervised learning, everything is IID, so identically distributed, isolated, distributed. So they're not correlated. But in reinforcement, and all your action is correlated. So once you deviate somewhat a little bit, and then as time goes by, the deviation can become confounded. And so when you deviate a bit more, so what happens is that action will take you to some states where you have never seen before. And all of a sudden, you don't know how to react because those states are not part of the training set. The only reason you experience those states is because you have a tiny deviation, maybe 20 steps before, but then you end up here, and then that's irrecoverable. So in those cases, supervised learning is not very helpful. So there are some solutions you can actually resolve the matter. One of them being you collect more data. Whenever you see states you've never seen, that maybe you can call some experts to ask them, oh, what happens if I experience this? Can you tell me how to recover? But that's very costly, and it's almost impossible in reality. There is another way, if allowed, you can run a simulation, so you can self-play to collect more data, and then hopefully the simulator portrays the reality to some level of as a quality. It's actually can portray the reality, but that's not necessarily true. And then that's where the self-supervised learning can be helpful. So I will talk about that maybe towards the end of the talk. So the 3 steps in our reinforcement learning approach is that we tend to adopt this model-based reinforcement learning. So essentially, we want to build a model of the system that either through a simulation or using the first physics principle, or maybe using deep learning to learn the mappings between the transitions between states. And then once you have that, you can train reinforcement learning agent. So we have an environment we build as a model, and we have an agent on top of it, and we train the agent offline so that agent knows how to act given a state. And then we can recommend actions and improve the model at the same time during online. So when you deploy the system, or maybe when you're in a staging environment where you can actually collect some data, not just from the simulator, but from the real world. So let me just go through the motivations for our approach. Then before we jump into those applications. So the first one is the model predictive control. So we think that the control community over the years have developed a lot of good techniques to deal with the unpredictability from your environment. So for example, in the model predictive control on the left, so the MPC controller will observe a series of measurements, and then based on these measurements, based on its understanding of the model, it will actually produce a series of actions, essentially optimal actions, at least based on what has observed and based on what's in the model. And then when you really interact with the real system, you only need to use the first action from. So suppose you have a series, maybe a list of 10 actions, 10 control commands, but you only exercise the first control as an input to the system, and then you measure that again. Then you get fresh observations, and then so basically you will discuss the 9 actions and use the first one, and then you go on to the next time step, and then do the same thing. So you observe the next 10, which and then you come up with another 10 actions, and then you only you use the first action to interact with the system and discard the remaining 9 actions. So I think that's quite an interesting way of combining the optimization and reality. So that's a model predictive control. And the other part is the what I call think fast and think slow. So usually in reinforcement learning, so the agent can be quite fast, because when you learn using this kind of policy neural network or value neural network to learn the mapping between your states to your action, or between the states to the position, to evaluation of that states. So this can be quite fast during inference time. So essentially you can think of them as kind of like a muscle reflex. But then when you're really doing something requires a lot of planning, those muscle reflex might not be sufficient. So you might have to have a high level plan. So let's say you want to go somewhere. If you want to grab something, you have a plan. You will move close to the table and grab your cup and grab your mug. And so there's a planning in your head, but the execution of those movements, this grabbing itself, they are complete fast muscle reflex. But how to string all these commands together, that's a planning. So there has to be a plan on top of the low level learned neural networks. So you can actually do a policy iteration, a policy search, in order to achieve the desirable outcome. So that this part is called think slow, and this part is thinks fast. So combination of the two, we believe can go a long way in terms of optimizing your industrial operations. So now we can talk about the, let me just move this across. Okay. So, sorry. So the first example is in a resource industry. We like to optimize the gas well pump. So these are methane gas wells. There are like thousands of them. So as you know that the gas will not, the gas and water, or the gas is actually constantly be under the hydrostatic pressure from the water, and then you almost always have to pump the water. Then the gas will come out into the well. But the thing is, how much do you want to pump out the water? So if there's an overproduction and underproduction problem, but there's a more complicated than that, because the pump speed is crucial. If it is too fast, then the pump itself will be worn out quickly, and often you don't have a very good understanding of its healthy status. So you almost have to exclusively rely on regular scheduled maintenance. And so if there's some issues with the pump, and they suddenly cause a delay or unscheduled outage, then that will be really costly. So you don't want to run it too fast, but you also do not want to run too slow, because otherwise the water will not come out, and then you will under production. And then, so working in the resource industry, we all experiencing the dilemma of accurately plan the production is actually not so easy. So in this case, the team has attempted using reinforcement learning. Then the idea is to train a very good water rate model, a very good pump wear model, and then combine the two, and then with some historical data, then that allows us to fine tune the speed of the pump. And so compared to previously, operated by the operators to optimize the speed. So using RL has certainly is able to scale the operations of thousands of wells. So this is quite exciting for the customer. And then just bear in mind, this is only one single variable, well speed, that we just use that as an example to fine tune it with RL. But there's like in the meantime thousands of different variables, and then so yeah, if you think big, there's a lot of opportunities there for RL to make a difference. So the second example is that we did some work with district heating in China. So where in northern China, where there's in winter it's quite cold, so the central district heating is actually quite widely deployed. And then the main issue is that they have a rather complex system where they have a main network, but also within each residential area, they have its own small water network. So by the way, these pipes of the heating, they're all running hot water. So 90% of them running hot water. And then, so obviously there's a lot of maybe hundreds or thousands of valves that you can control. And then the issue seems to be that the operators sometimes cannot accurately predict the weather condition. So if suddenly the temperature dropped and then there's a lot of complaint, but it's not it is not warm enough. But sometimes when nobody's in the building, then it's still quite hot, which is just a waste. You definitely want to reduce the waste because most of these heating systems are using the coal to generate the energy, the heat. So yeah, so the first thing we have done is actually develop a good demand forecast, and based on various factors, including the weather condition. And so once you have the load, the demand, and then you can actually optimize. And you can do a simulation. You can optimize for the valve control. Yeah, so we tested out on one particular region, and it was quite positive, the feedback. So that's a second example for using RL for district heating optimization. So the other example, which is probably quite common these days, is the air conditioning. So most of these buildings, current buildings, 70% of energy is consumed by air conditioning. So HVAC, what to call. And so the idea here is, again, to build a demand to model the demand, the load of the system. So in that case, we actually build a digital twin in order to model the relationships between the demand and also the efficiency of the AC units. Turns out that that's one of the crucial metrics. And then once you have this digital twin, you can predict the demand based on the temperature, the weather, but also many other factors, including the layout. And then you can have a good control as to which units you wanted to shut down when you know that it's not going to be efficient if you continue to run those units. So it turns out that can reduce the loss of cost without compromising the air conditioning effect for the building. So yeah, so that's another example that we did using RL to do such industrial control and operations. So now I wanted to draw your attention to a different sort of problem, which is also industrial operations that we did for our customers, but we have built a open source solutions for that, and then released to the open source community recently. So this is a well-known traveling salesperson problem. So basically, given a list of nodes and cities and their distances, you wanted to find out the most optimal shortest path, or maybe the lowest cost path, visiting each city nodes only once and return to the original. So it has a lot of applications in order repicking, in warehouses, logistics, transportation, DNA sequencing, and the manufacturing. So on the left, you can see here is an example of PCB board, where you have like more than almost 6,000 of holes, and how to drill this hole in a more efficient manner. Essentially, it's a TSP problem. You have to drill such thousands of boards, and each one of them has thousands of holes like this. So it's really important you get the most efficient way to print it, to draw the circuit board. And on the right hand side, you can see the solution that we did for one of our customers to help them optimize their routes. So the TSP problem itself is a hard problem, And if you wanted to do an exhaustive search, the complexity is like factorial. So factorial, by the way, it's actually growing much faster than exponential. Maybe initially similar, but in the end, it's much quicker than exponential. Normally, we are saying exponential is big, but factorial is huge. So that's so it's not going to solve the problem if you do a exhaustive search. There are many solvers in the past, but in this case, we're using a reinforcement learning combined with a graph neural network to solve the problem. So initially, Joshi et al. They have released their solution as open source, and then we built on top of their solutions, and then added a distributed training and various different things on AWS platform, and we also contribute back to the open source. So just one more slides on that. So the idea is also you can actually bend a lot of problems into the setup of reinforcement learning. Right? So in this case, the agent is basically trying to figure out what will be the next connections between some pairs of nodes. So that's actions. Essentially, you have many different actions can take, and then the states will be the embedding of these nodes, and these nodes originally have like 2D coordinates, but you can learn embedding around a hidden space and high dimensional, and then with this embedding, and then you can allow the agent to take actions. And so in order to get some reward, in this case, the reward is essentially the tour length or the cost associated with the tour, and various of constraint or penalties. So yeah, so whenever you have states, so what happens is this particular policy network we're using reinforce. It's a very old algorithm. It's under the family of policy gradient. So here I'll just show you the equation of policy gradient, and then so what happens? This is the probability, and then this is the action given the states, and that's your reward. So so the idea is to maximize this likelihood if your reward is positive. So yeah, so if your reward is positive, then the way to maximize this log likelihood is to increase the probability here. But if your reward is negative, then the way to maximize the log likelihood is to minimize the probability here. And so that works out. So positive reward will encourage the network to learn its parameter role such that next time these kind of actions will be encouraged. And so this might sound a bit crazy, because then when this will actually learn anything. So turns out that if you learn this for somewhere between 10 to 100 million times of the different problems, it's doing a pretty good job. So the lessons learned from all these different exercises of reinforcement learning seem to suggest that human factors still are the key. So in many cases, what we have recommended the system, recommended operators to do, only portion of them are really taken seriously by the operators. That's because some of these are counterintuitive, because we are optimizing long-term reward, not necessarily immediate reward. And so yeah, so there's a bit of a pushback, if you like, and so I think it's really important to work with the operators and then constantly seek their feedback, and then demonstrate to them how the system works. So to do that, we actually developed various different consoles. It's most like a game consoles, and to simulate those operations as a game, so they can play those games, and then eventually they can learn more about what those actually means in terms of long-term reward. So yeah, there's a big change management, but so including all the training and understanding the method and the purpose. So that's not to say that these are all non-technical. This still can be very technical while you are incorporating the human factors. And so just to give you one example, this is something quite interesting. So we all know that RNA folding is important to drug discovery. So the recent protein folding seemed to catch a lot of attention within the community. But RNA folding is is somewhat similar. So basically, the 3D structure of RNA of molecules, those structures determines the properties of the functions of the RNA. So how they fold is actually matters a lot, given the same sequence. So here is a project that people have been applying reinforcement learning for RNA folding. So the idea is how to work with existing software, existing folding software that have been developed over the years, and that has a lot of expertise in it. And so when we come up with new actions or policies from RL, you don't want to completely ditch what we have done in the past. So how can we incorporate those knowledge and bring on those expertise within RL? It's a challenge, but this particular work has provided a very good example of doing exactly that. So essentially, so as you can see, a long-term decision making is almost like a tree. So each node here is a state, and then for each node has a branches, and each node, and then the following state has also its own branches. So most of likely the tree is actually quite huge, right? So you can imagine if you have 200 states, each state have like even just three branches, and then the possibility is a 3 to the 200. So that the combinatorial it comes in here. But the way this can be done in a more approximate and a fast way is using existing software to approximate the state's value here. So you can using existing folding software to run what happens after the states k+1. But then you only make a decision on the first step here. So suppose you already have completed your folding up to states xk, and then you do a one-step look ahead and try 3 different options, and then the rest of it you don't expanding them anymore. You just use existing software to do it. And then so what's end up happening is that you are actually combine the one-step look ahead plus your heuristics. And in the end, you're using another RNA folding expert software to compare the different solutions and then to get the best one. And then you do this for each stage of your tree. So but like this, you actually incorporate a lot of the expertise from the community. So that's a very good example about seeking feedback and integrate it into your reinforcement learning training process. So the second part is about the self-supervised learning. And so you might have heard a lot these days. Self-supervised learning has been termed as the dark energy of the intelligence. So the idea is to we have a ton of raw data, but we don't have a ton of label data sets, and that's just because it's very costly to make them. So how can we actually make most of those raw data if they haven't got any corresponding labels? So the self-supervised learning said, well, you can actually learn some proxy tasks which has some cheaply obtained labels. So, and then once you have that, let's say we have those labels, then we can learn a general purpose representation. So as you know that deep learning is all about representation learning, and then So those representations can then be used for downstream tasks. So this has been done. So this kind of labels has been done in multiple modalities, so including computer vision, language modeling, and speech recognition, audio processing. So the idea is the simplest idea is generative reconstruction. So basically, you are just randomly mask some tokens on your sequence, or maybe you can chop. So you have one sentence, you could chop the other half, and then let the system predict the second half, or maybe the first half, or maybe just randomly mask a few tokens and let the system predict it. And then you do this for millions and millions of them. And that's one way of doing it. The other way is called discriminative. And then, so this contrastive learning has been really interesting recently. So the idea is that if you have a one image, and you can just crop it somehow, maybe, and transpose it, crop it, or do some transformations on it, and then what you end up is a new image. But you know that this new image is associated with the original image. And so this pair of images have some relationships. Now you have a randomly chosen another image, and you know that randomly chosen image most likely has nothing to do with either one of these two images. So based on those relationships, you can actually train your neural network to maximize the agreement between the original pair, and then to minimize the similarities between that one pair and then the other image. So I'm not going to delve into too much about contrastive learning, which is a different topic, very interesting. But I'm going to more talk about the reconstruction using in the self-supervised learning. So especially for NLP and speech, because that's one of the examples we've been using it for our industrial operations. So as you might know, that the transformer has ruled a lot of the sequencing modeling tasks, including language modeling, but also speech here. So the BERT model that originally proposed, so is actually doing exactly the pre-training on the self-supervised learning. So it is basically randomly mask some tokens, and then once you mask it, and the model is asked to predict, to classify what's the missing token, and then because you already know the ground truth because you masked it, and then you can just compare the two classifications using some cross entropy. So this is nothing special. It's just a normal classification, essentially. And because this is classification, so it's actually not so hard to calculate, and it's very fast as well to train on large scale. And then the other idea is to learn the sequence. So you have two sentences. Originally, they are in this paragraph. So, and now basically what you can do is you randomly swap them. So sometimes you don't swap them, sometimes you do swap them. But when you do, you put the label as no, that's not correct order, because you have to swap them. So the only thing that the network is asked to do is classify whether this two sentence is a natural sequence or not, and to learn essentially to learn the sequence between the two, rather than just the content. So that's you can see these labels are very cheap. They can very cheaply obtain, but it turns out doing such thing has a very profound effect on the downstream task. So here is another AWS AI researchers have been working on. So apply the similar idea, but on the speech signals. So instead of having a token, you have a filter banks, and then you can do the similar things and let it just mask out a section, and then let it predict what's in the section. And so that's kind of interesting. This gives us a framework to do self-supervised learning. So the business problem is that we have an instrumentation scattered around a large chunk of land, and then so this instrument has sending these vibration signals collected by thousands of IoT devices. And then, so the idea is we wanted to know whether some sections of instrument has a fault that needs to be, its component needs to be swapped out in the next scheduling time. So that essentially is a predictive maintenance problem. And the data is actually the instrumentation vibration signals. And then, so we applied the machine learning approach, especially the self-supervised learning plus transform learning to tackle the cold start issue, where initially you don't have a lot of ground truth labels, because collecting those labels is really costly and time consuming. So just to give example, if you have a long range of signals of vibrations, perhaps when you collect the ground truth, you have to arrange some maintenance to go there to collect the ground truth. And when you do that, it's only maybe several hours in a day or something. So maybe just several days within maybe 3 days within that week or within that month. So the label data is actually quite tiny compared to large data sets which has got no corresponding labels. So that sounds like a good fit for SSL. So that's what we did. We actually applied the SSL. So we're doing the original signal. We extract the signal in a feature space, and then we start to do a representation learning. So essentially, learn to predict part of the feature from the other part of the feature without any labels. We just chop some of the features and let it predict it. And then as a result, we were able to learn the feature representation, and that representation will be used for downstream tasks, for supervised learning, for transform learning, in this case, supervised learning. So then during the supervised learning, you use the raw signal again. So combine the two, you can get some good outcome. In fact, it's 10 times better than you directly using signals, because directly using supervised learning, because you don't have lots of label data. So essentially, you have to discard the data. They're not useful, which is not labeled. So that I think that lastly, I'd like to highlight there's a connections between SSL and RL. So essentially, you could using SSL to learn the representation in your simulation, and then once your model learn a lot of the representation, you can apply the model in reality, and you only need small amount of label. So what they call zero shot or few shots or domain adaptation, so that the model that you learned from your environment is not wasted. It can be reapplied in the reality by giving it a few examples with label data sets. So that's one way of actually strengthening your simulation to make it more real. So the sim to real is has tried a lot of body of work recently. So I think so that summarizes the talk. So we have briefly gone through reinforcement learning, Markov decision process, and we have shown several applications of RL in industrial settings. We understand that it is important to keep the human in the loop, and there's also can be quite technical in incorporating human feedback in RL training. And we also covered the self-supervised learning and given an example. And also in the end, we highlight the connections between self-supervised learning and reinforcement learning. Yeah, I will stop there and maybe take some questions.
Thank you so much. Thank you so much for sharing. I hope everyone has some takeaways. So now we're gonna open the Q&A section. If you have any questions, please feel free to post it in the link or in the chat box. And if you prefer to speak, you are feel free to raise your virtual hand as well. And I will probably share my screen.
Yeah, sure.
Yep,
So
to see.
I just saw one question about the difference between unsupervised learning and self-supervised. So yeah, they all look similar, but there's a key difference is that the self-supervised, you are still running a normal supervised learning. So you are still using the cross entropy and all that. So there's a goal, there's a target. Whereas unsupervised learning, it does not target. It's hard to get the target right sometimes. So the only difference between self-supervised and supervised is that the label is somehow generated in a very cheap way instead of going through the normal manual labeling process. So it is. So I would suggest that we draw a distinction between unsupervised and the self-supervised.
Okay. So we've got the first question asking if you will be able to share your slides with the audience.
Yeah. So that we can organize with you maybe.
Yep, that would be great. And then the second one is there any connections between the TSP and DNA sequencing?
Yeah. So there's definitely a connection, but because I'm not a DNA sequencing expert, so I would not want to comment on too much. But every time TSP problem shows up, there's a DNA sequencing as one of the classic applications. So I have not looked at it myself into it, but yeah. So it seems so, but I cannot give you more insight on that. Sorry.
Yep, that's fine. And then there's another one saying that is there any resources you use to learn RL or SSL?
Yeah, good question. So SSL is really new. So it's like proposed in 2000, maybe 1918, but back in the days when Hinton has the first paper on SSL, this kind of idea of regenerate something to reconstruct something. So SSL is really hard to read papers. I have not seen a good, maybe there's some workshop on SSL, like Europe's every year they have SSL workshop. There's some surveys on that. So yeah, SSL, you have to really grab some latest paper to read. So the few papers that I highlight there, I think they are a good starting points. And then RL is RL. I think there's one tutorial I think is really good is from UCL from David Silver's tutorial course on reinforcement learning. And yeah, so that one is a classic. So it's released on YouTube, and so maybe have a look. So that one has gone through the book written by Sutton. So Sutton has a book on reinforcement. It's a classic reinforcement learning. But David's lecture coupled with that book will be really good. And I understand there is another Coursera reinforcement learning. So that's also surrounding Sutton's book. So yeah, so those are definitely worth looking into.
Yep. I guess we don't have any more questions for now, but if anyone has any more questions, please feel free to type in the chat box or submit in the link or just raise your hand and speak. But yeah, I think it's really interesting talk. Thanks for sharing for the use case in the industry for using reinforcement learning and SSL as well. So yeah. Oh, we see there's a raised hand. So yep. I'll let you to unmute and ask. Yep, go ahead.
Yes, hi. This is Renee here, Sydney-based. Thanks for the talk. That was a really good one. I just wanted to understand in terms of the cost management, because I'm assuming you probably have run all your work and experimentation on AWS. So how did you manage with infrastructure, cost involved in all of that?
Yeah, thanks, Renee. Yeah, so we used so that's one of the reasons actually we wanted to reduce the cost of training RL. That's one reason we use this distributed training library come with a SageMaker. So instead of running a sequential training, which takes a long time, so it's the same instance, but you can have a speed up maybe by a factor of up to 8, depending on how many GPUs on your machine. So yeah, so that's one of the reasons we basically restructure the training process so that we use the more efficient way to train it, so that you can you can reach the level quickly. Yeah, so mostly our training was all done on SageMaker, and there's a distributed training library there, and with all these other associated features such as metrics tracking. So one thing you really want to track the reward, long-term reward, so that this goes down. So if you see the cost or the reward is going up again or fluctuates, then you know there's something wrong. Then you can quickly terminate that and then refine-tune your parameters. So yeah, I'm afraid that this RL itself currently is still in a regime where you have to do a lot of hyperparameter tuning. Yeah, so with some handy tools that can always give you some insight without you having to digging out into the logs, that would be really good. Yeah.
Yeah.
Yep.
Okay. Cool. Thank you.
Yeah, we've got a few more questions coming up. So this one is asking, are there multiple steps before you know if you got a reward? How do you decide reward for earlier step?
Yeah, so that's a very good question. So I think what happens is this is a sparse reward problem, so you don't have a lot of reward. So let's say we have a chess or something, right? You don't have any reward until the end. You know, oh, I win. Oh, I lose. So one thing you can do is that you can still learn the effects of action just based on the final reward. So that you can still do, but it's definitely not very efficient. By the way, that's exactly how we did it for the solving the TSP problem. Because when you are connecting all the dots, you don't have any rewards. You don't know how I'm doing now, but you only know the final cost when you finish the last dots, and then you can then reverse that back. So going backwards to see which action has played an important role in generating the final reward. So that you can still do, but it's going to go through a lot of training steps, as you can imagine. So that's a credit assignment problem. And the other solution you could do is you generate some artificial reward, so like a reward shaping. So that's how when you design an environment, you know that like when you're driving a car, actually nobody tells you how well you are doing, but if you are observing that your car is always in a lane or something, right? So within the lane, whenever you hit you somehow you hit a lane or something, then you can get some penalty, right? But that's just one example. So you could using some other alternative way to give some staged reward to system, but reward shaping is a kind of very it's an art. So it's actually does no a good disciplined engineering know-how to tell you how to do that. So it really depends on your understanding of the system and your understanding of agent and the network. So hopefully, when you give it a reward, you can learn something. But if you give it too frequent or give it something which is not really towards the final goal, then your agent become very smart to learn some shortcut, and then then that's not good either. So designing a reward mechanism, it's very similar to human learning. So when we go to college, universities, or high school, the teachers have designed a curriculum for us. So it's not like the teachers say, well, you have to finish, you have to graduate 6 years later, and that's the end goal. So every year, every term, the teacher will give you some study curriculum to study, and then so those are those can be considered as part of the reward shaping. So hopefully eventually you will graduate and become qualified qualified graduate, having possessed all the knowledge that you're supposed to learn. Yeah, so that's a good question. Thanks.
Yep, that's a good answer as well. And also we've got a next one is, what's the most used AWS service when you use SSL? Yeah, so I was going to talk about that because there's time limit. So we used we used the still SageMaker. So the reason when we use SageMaker is because because the data is actually large volume. So this vibration. So the frequency is actually in a kilohertz. So that means 1 second you have thousands of points, maybe tens of thousands or something. So there's a lot of data, and then but imagine you have to go through all of those data to learn something, right? So because SSI is all about learning raw data. So at the time, there's one I/O mode for SageMaker. It's called pipe mode. So you can actually pipe the data directly from S3 buckets directly to your GPU without touching anything else, without going through your local file system, without going through any cache or anything. So that's really useful because we did test that when you go through some handovers, file systems, your speed is dramatically slowed down, and then your GPU is not utilized. So that's the reason it has but just two days ago, I think SageMaker has a new mode. It's called fast file mode. So that's even better because you don't actually need to do any pre-processing to make it a pipe mode working. You can just treat it as a normal file, and then it will stream to your GPU like as if you are using a normal file. So I think I would say that the reason which we have used SageMaker for SSL is only because given the large volume data, given its I/O capabilities. So I think we're pretty happy with that choice. What else? So that's just training the model. But then when you really rolling out your pipeline to production, so there's many choices. So I think on Thursday there's another talk from AWS on using SageMaker pipeline to streamline your workflows. So maybe you can attend that. That's give you more detail. But in the meantime, within the AWS ecosystem, there's step functions you can use as well. So you can orchestrate your training inference pipeline through step function, and each component of your pipeline is either SageMaker training, SageMaker inference. So that's how you construct a workflow. Hopefully that answers your question. Yep, so we will take the last question for this one. So due to the time limit, so is reward shaping an alternative to the credit assignment problem or a solution for it? I'm not so sure. I understand. So I would maybe it's more like a workaround solution. So it's
I would say it's a solution. Credit assignment has never been easy, and the entire neural network, gradient descent is all about credit assignment. So I think that the reward shaping it's a one way for dealing with the sparsity of the reward signals, because you always have to have signals to learn something useful. But if your signals are very sparse, so that meant that you have to collect a lot of data. So if your signals is 1%, then to get 10 signals, you need to, 100,000, right? So 10,000 instances. So that's the reason about reward shaping. But maybe not necessarily an alternative to credit assignment problem. It's more to do with solving the reward sparsity. The credit assignment problem is a bigger, more problem in a bigger context, I would say. Yeah.
Right.
Thanks.
Okay. There's actually one more question in the chat. For you to confirm the lecture that you mentioned earlier. Is it the link that posted in the chat?
Yeah, I'm just double check. So this one is 2021. So the one that I looked at is David Silver's 2015. So let me just.
Yep. So probably another one.
Maybe you can check this one. Let me just double check. Yeah, so RL course, we'll put it here. Yeah, I think that's one I use it to get started.